Hey everybody, Dr. A here, and in this video we're going to be exploring a column buckling example. So let's go ahead and get started. Given to us, we are being told that a W8 by 15 steel column is 10 feet tall. It's fixed at its foundation and pinned at its top. We're being asked to sketch this, and then we're being asked to compute the allowable, that's an important word there, allowable Euler buckling force using a factor of safety of 1.67. So let's go ahead and get started, all right? So under solution, the first thing we're gonna note is where do we get the section properties of this W8 by 15, okay? There are lots of sources that can give you cross-section properties of a steel W8 by 15 column. I'm gonna go ahead and summarize them for us right here. So for a W8 by 15 steel column, we have the minimum radius of gyration, which is R sub y equals 0.876 inches. And we have the cross-section area of 4.44 square inches, okay? Now, the next thing we're being told is that the column is fixed at its foundation and pinned at its top, okay? What does that mean? That means the effective length factor, K, is 0.7. So if we want to sketch this like the problem asks us to do, we're going to have a pin at the top and we're going to have a fixed connection at the bottom, okay? And the total length here is L equals 10 feet. And just to get my units straightened out, I'm going to go ahead and convert that to 120 inches, okay? So if this thing wants to buckle, how is it going to be shaped? It's going to come out from the pin connection, and then it's going to taper down to that fixed connection. So that's going to be the buckled shape, okay? Next is how do we actually calculate what we're being asked to calculate, right? We need the allowable Euler buckling force, all right? So if you remember, when we say allowable and we're given a factor of safety, we're going to have a P allow, and you take that buckling force, P sub E, that we're going to calculate here in a minute, and what do? Well, we divide it by that factor of safety we're given, okay? So this idea of a factor of safety is something that we discuss early in a mechanics of materials course, all right? So the task now is that we need to compute this Euler buckling force, okay? So the question is, how do we do that? Well, we had two governing formulas that we could use, right? One of them is P sub E equals pi squared E I min over KL squared, okay? So that's one version of the formula where I min is the minimum radius of gyration, right? So we said I min is equal to the minimum of Ix and Iy for our purposes for this topic in mechanics of materials or structural analysis introductory type of course. All right, so can we use this formula right now? Well, we could if we had I min, or if we had, access to Ix and Iy, but I gave you the radius of gyration here, all right? So that means that we need to use the other version of this. So the other version of this formula would be pi squared EA over KL over R min squared, okay? So again, if you watch the background information video on this, you have both of these formulas that will give you the exact same thing. It just depends on which cross-section material or cross-section properties you have access to, and then you can use whichever formula you want, all right? Now, I'm giving us the radius of gyration in the cross-section area, all right? Which means we're going to use this second version of the equation here, all right? Now, we also said that the material was made of steel, and do we know the modulus elasticity of steel? Well, hopefully we do by now. The modulus elasticity of steel is 29,000 KSI. That's the safe bet to use for modulus elasticity of steel unless you are deliberately told something different, okay? So if we substitute these values in, we're going to have P sub E equals pi squared times 29,000 KSI times the cross-section area. That was 4.44 square inches, all divided by 0.7 times 120 inches divided by that radius of gyration, 0.876 inches. And then we square that whole term in the denominator. So if I were you, I would punch this through my calculator and make sure you get the same answer as me. Be very careful here. The pi is squared. That's an easy mistake to make. Also be careful here, 0.7 times 120 inches. You need to have consistent units here. Don't use 10 feet here if you're using KSI and inches squared and inches for radius of gyration. Convert that 10 feet to 120 inches, and then you got to square that whole thing in the denominator. So if you punch this through carefully, you should get 138.2 kips. Now, that is the force that causes buckling. So we'll make a note here. This is the force to cause buckling. Okay? Now, the problem asked us to find the allowable force. So that means we have to build in that factor of safety to give us a little safety cushion room there so the column won't actually buckle, right? You don't want to design or take your columns all the way up to right about to buckle, right? You want to have some safety in there, right? You don't want to get to the precipice of failure. So you build in a factor of safety, right? And so that's what we're going to do with P allow. And so that's going to be the 138.2 kips that we just calculated divided by that factor of safety we were given, which was 1.67. And our final answer is 82.8 kips. So what this value represents is the force that that is taking the buckling force and scaling it down, right? So what we're going to say is, hey, to be safe, to prevent this column from even coming close to buckling, we are not going to put more than 82.8 kips on this column, okay? We want to have plenty of safety in this column such that it's not going to even come close to buckling. So we're going to build in this factor of safety, and this is going to be what is known as our allowable Euler buckling force, okay? So that concludes this example. If you found this helpful, please hit like and subscribe. Thanks for watching.